Welcome to the next Infosys seminar. It's a pleasure to have Professor Murch from Washington University in St. Louis. Kader is a good friend and we were postdocs together at Berkeley. But Kader did his undergraduate degree from Reed College and then his PhD was actually in cold atom physics in the group of Dan Stampecker in Berkeley as well. And the weather in Berkeley was too nice, so he didn't want to leave. And he just hopped over to Irfan Siddiqui's lab, where I was also a postdoc. And I think maybe you joined a year after or 6 months after I did.
Yeah.
And we had lots of fun working on projects. And I think, in fact, his first project we worked together on using nonlinear resonators in superconducting qubits and looking at a phenomenon called what do we call it?
Autoresonance.
Autoresonance, that's right. And then after his postdoc, he joined Washington University Physics Department at St. Louis, where he now has his own lab, where they have again superconducting qubit architecture, but they have been heavily focusing on quantum measurements and looking at how to use peak measurements and strong measurements in various regimes to look at very interesting, a lot of fundamental questions about quantum mechanics. So really exploiting the flexibility this technology offers us to look at some basic physics. And today he's going to be telling us about some new results they have got in the past year. So welcome, Kader.
Thank you, Vijay. Thanks for the wonderful introduction. And of course, Vijay taught me everything I know about anything here. As he mentioned, the first project we worked on together. So I'm very thankful to Vijay for what we've done. So just because we're far away from Washington University in St. Louis in the world, I just thought I'd tell you where this is. Some people who were at the meeting last week saw this slide, but it's the only slide that will be repeated. It's in the middle of the United States, here in Missouri. We have another person from WashU in the audience, this is Casey Wagner, so someone else knows where it is. It's famous for having this beautiful arch. Just like you guys have an arch commemorating, I guess, British coming here. We have an arch commemorating people moving from the East Coast to the West Coast. And it's a wonderful weighted inverted catenary. And as Vijay mentioned, we do experimental research with superconducting qubits focusing on measurement, so thinking about quantum trajectories. I'll talk today about Zeno effects, which is kind of a fun project. Thinking about funny things like, what if you ask questions about the past in quantum measurement? So smoothing and retrodiction and all sorts of strange stuff there. I'll also talk about metrology, about our recent work on frequency metrology, measuring frequencies. And then we're also trying to get involved in quantum thermodynamics, thinking about heat and work and so forth. So that's what we do. The outline of the talk, I called it, what is it they call this talk? It's called it controlling with measuring and measurement and measuring with control. It's kind of a shameless approach to try to stick two topics into one talk. But I think they fit together into a theme. So the first thing has to do with frequency measurement. So this is how to measure things with control over quantum systems. And the second part has to do with Zeno effects, sort of how to control things with measurement. So they have to have two different pieces. The first part is maybe a little more technical. I figured I'd take advantage of, typically in a seminar, you're a little more attentive at the beginning. The second part has movies and it's kind of fun. And so by then you'll wake back up. So that's the plan. Feel free to interrupt me at any point in time during the talk. We can have this be as informal as you'd like. Okay. So first thing we'll talk about is this crazy titled thing, adaptive optimal control for quantum enhanced frequency metrology. But before we get too far into that, I want to just reflect on what makes quantum mechanics special. And I'd say that it's summed up in sort of one concept, which is non-locality. So what do I mean? Well, we all know about Bell's inequalities, or maybe we do. Bell's inequalities is a test of locality in some sense. So in the macroscopic world, we have local properties. So something, this clicker is pointed up or it's pointed down, but that's a sort of local property. It's not, it's not entangled with something. But in the microscopic world, we have this quantum entanglement. Okay, so quantum mechanics is very different than the classical world, and this is sort of shown in the violation of Bell's inequalities. So that's non-locality in space in some sense. But there's also non-locality in time. And this is characterized by maybe a lesser known inequality, which is called the Leggett-Garg inequality. And this sort of tests the idea, do quantum things have definite properties? Or do they have indefinite properties? So in the macroscopic world, things have definite properties. In the quantum world, we have quantum superpositions. So those are the two aspects of non-locality you have in space and in time in some sense. And I'm going to just keep this in mind as we get into asking questions of how can you measure things, or what are the quantum limits? How does quantum mechanics help? I'll try to show that both of these properties give you advantages in quantum measurement, quantum metrology. So, okay, frequency measurement. That's what we're going to talk about. I just want to make the case that frequency measurement is important, right? So a frequency measurement is the basis of clocks, which were originally the basis of navigation. How do you know where you are when you're out in the middle of the ocean? Well, you can know what your latitude is by looking at how far the North Star is off the horizon, or the Southern Cross in the southern hemisphere. But to know your longitude, you need to know what time does the sun reach its zenith. And so in order to know what time it reaches zenith, you have to keep track of the time. So really coming up with good clocks enabled navigation further from the coast, so you could see, kind of figure out where you were in the world. It's also the basis of GPSs, which is how we navigate around these days. But beyond just navigation, frequency measurement also has important aspects in fundamental physics. For example, think about the spectra of some atom. Okay? You can measure the frequencies of these transitions, you can compare them to theory, and you can see that there's some deeper physics, or that your initial model didn't work. So in hydrogen, you have this very simple closed form solution, but then you look more carefully, and there's fine structure, there's hyperfine structures, there's a Lamb shift. You learn a bunch of physics by just measuring frequencies very accurately. And ultimately, frequency measurement is really the best practice for any measurement. So when I was a young experimentalist, I can't remember who told me this, but someone said, if you're going to measure something, make it a frequency measurement. So whatever you want to measure, try to figure out a way to turn it into a frequency measurement, because frequency measurement is sort of the best way to measure something, measure frequency. Yeah, so for example, our current frequency standard, which I think is still the case, the atomic clock, will soon be supplanted with maybe an optical lattice clock, which will work on a similar principle. But the atomic clock is based on the measurement of the energy difference between two hyperfine states in a cesium atom. Okay, so we have these two hyperfine states, F equals 3, where the electron spin and the nuclear spin are anti-aligned, and F equals 4 state, where they're aligned. And these two energy states are separated by an energy of around 9 gigahertz in frequency units. Okay? And so what we're basically doing is just measuring this energy difference. And if you want to think about how accurately can we measure this energy difference, or the frequency of this transition, well, we can turn to the energy time uncertainty principle, which is delta E delta T is greater than or equal to h bar over 2. So this means that the frequency uncertainty, delta omega, is going to be 1 over 2 times the interrogation time. So the reason why this is a good frequency source is because these two states can live for a very long time. Okay, so you can measure for a long time. And the point I really want to get across is that the frequency uncertainty goes like 1 over t. And I want to just embed this in your brain, because that's what is always the case. Any sort of sensitivity usually goes like 1 over time. Another way to say this, so that means longer time means better accuracy. Another way to say this is, say we take some signal. Okay, here's a sine wave. Frequency happens to be at 13.4 hertz. Sampled for 1 second, and I take the Fourier transform of it. I see, look, there's a peak at around 13 hertz. But you see the width of this is proportional to 1 over time. So it's actually 1 second, or 1 hertz is the width of this peak. In fact, the spacing between points in the Fourier transform is just 1 over t. So really you'd think that 1 over t is the best you can do in the sensitivity. So you want to know what the frequency is, you just sample longer and longer. Can I have some nods of the head? Does that make sense? No? Yeah? Okay, you agree? Good. Because the reason I want to make this point is because I'm going to show you that this is not always the case, and that you can beat this with quantum mechanics, which I think is pretty tremendous. Okay, so how do you measure the frequency of an electromagnetic wave? Say, for example, this, say, if you got the cesium atom to emit a microwave photon at that frequency. Well, it's easy. You just you know that the frequency, or the total phase, is the integral of the frequency times the time. So the frequency is the phase divided by the time. So you just count up the phase. There's like, where's 1 pi, 2 pi, 3 pi, all the way up to like 26 pi. And you divide by the total time, and that gives you the angular frequency. Okay? So the longer you measure, of course, the more accurate you are because you're dividing by a bigger number. And ultimately, you're limited by how well you can determine the phase at some final time, or this phase difference. Okay, so how accurately can you determine the phase? Well, we think about the quadrature space of the electromagnetic field. This is some sort of electromagnetic wave. It's going to be in a coherent state, a minimum uncertainty state. So if the amplitude of the field has a sort of square root of n dependence on the photons, the electromagnetic wave is described by some minimum uncertainty blob here, which means that if I were to determine the phase, I would be limited sort of by the size of this blob in my accuracy. Okay, so since the length of this is square root of n, then the phase uncertainty goes like 1 over the square root of n. This is just a shot noise limit, right? And I'd say that's sort of the standard quantum limit. This is what happens when you try to measure the phase of a laser or something. That's as good as you can do unless you're really crazy. Okay? Yeah, so if you're crazy enough, you can try to harness further tricks in quantum mechanics, that is entanglement. And you can squeeze this uncertainty state so I can reduce the fluctuations along one axis while increasing the fluctuations along another axis. In which case, I can get better phase sensitivity, in which case the ultimate limit is the phase uncertainty goes like 1 over n, the number of photons. Okay? So this 1 over n is what is often kind of called the Heisenberg limit, or the ultimate scaling, the best you can do, no matter what. And you only get that when you entangle all of these n photons together. Okay, so quantum entanglement gives you an improvement over no entanglement. You go from 1 over n, square root of n to 1 over n scaling. And this is kind of an exciting idea, is going to soon be employed in enhancing the sensitivity of LIGO's gravitational wave observatory. So it's very practical. So we can think about these sort of two resources in measuring a frequency. I told you that the longer you measure, the more sensitive you'll be. So that's what I'd call the serial resource. And the more photons or something you have, or the more quantum systems or whatever you want to do it, or the more times you make the measurement, that's the parallel resource. Those are the sort of two things we have to play with. So you can like measure longer or have more things to measure. Okay, so I just told you that for this parallel resource, the sensitivity is normally like 1 over square root of n. With entanglement, you can achieve 1 over square root of n. With entanglement, you can achieve 1 over n scaling. Okay, and then I told you that with time, this serial resource, the sensitivity goes like normally 1 over t. But what I want to show you today is that if we harness the other piece of quantum mechanics, which is superposition, that is coherence plus some control, we can achieve a frequency sensitivity that scales as 1 over t squared. So we have these two things that are funny about quantum mechanics. We have superposition and entanglement. Entanglement gives you this. Quantum superpositions give you this, if you use it properly. So that's what we've done. And this is based on a theory proposal by our colleague Andrew Jordan. And we sort of demonstrated that it actually works. Okay. So before we get into the details of that, let me teach you some terminology about metrology. Okay, so I think this is kind of maybe useful to think about how one quantifies how you measure things accurately or something. So say we wanted to determine some parameter omega. Well, we don't just measure the frequency. The frequency is not something you really can measure. You measure something else. You measure the phase you've accumulated over time. You don't, so actually what you measure is some sort of parameter x. So it's abstractly. And x is going to follow some distribution that hopefully depends on the frequency. So going back to our example of determining the phase of some electromagnetic wave, we don't just measure the phase, we actually measure, say, some quadrature amplitude. What is the amplitude of the wave in phase with some oscillator, reference oscillator? Okay, so what we have is some probability distribution of this quadrature x2, and that's going to move around as the phase moves. Okay, so we measure x2, and we infer information about the phase. Okay, so in that case, there's something called the Kramer-Rao bound, which is a bound on the mean squared deviation of some parameter And it follows this form. Okay, so the variance of this parameter is always going to be greater than or equal to 1 over d, which is the amount of data you have, times I sub omega. And I sub omega is the Fisher information. So Fisher information is related again to these probability distributions. It says, how much does the distribution change as you change the parameter you want to estimate? The more it changes, the more Fisher information you have. The less it changes, the less Fisher information you have. So these seem like reasonable parameters. So we have this concept of this Kramer-Rao bound. You can only do this good. And this depends on how much Fisher information your measurement has about the parameter. So yeah, so this depends on this distribution. The more it changes as we change our parameter. So here the parameter is g, something more abstract. We take kind of see how this distribution changes, the larger the Fisher information. And I'll give you an example of this.
So here,
yeah.
Are you talking about the value of px2 changing or the distribution itself changing with some parameter x?
You're talking about how the distribution changes with the parameter. So how does this distribution, p of x, depend on the parameter g? So somehow I forgot to change this to omega.
Yeah.
But if I change some parameter, how much does the distribution shift?
Just like how much is it broaden, or like does it actually take on a different form?
How much does it take on a different form? So for example, if I think about this phase thing here, if I think about this parameter x2, it has something there. If I change the phase, then that is going to shift the distribution relative to it. And so I'm just curious, how much does the distribution shift? If it shifts a lot, there's a lot of Fisher information. If it shifts not at all, there's no Fisher information. Okay. If there's no Fisher information, then the variance of this parameter is infinite, and we learn nothing. Good. Okay, so that's kind of the classical case, even though I'm talking about this sort of measuring a coherent state. In the quantum case, we have to revise the definition of the Fisher information. So there's something called the quantum Fisher information. And it's expressed in terms of this thing called the Boris distance